So anyone that just saw what to expect when you're expecting presentation down the hall, that'll serve as a great segue into this presentation, which apparently we're in the final four for longest title of presentation amongst those here yesterday and today. We'll see where that ends up. Just briefly, we're going to provide a cursory overview in the time allotted on integrating building energy modeling, et cetera, EMIS and commissioning. There is an article in the spring journal of the Tab magazine that goes into a little bit more detail. So that said, I would suggest good morning to all, and thank you for attending this presentation of integrating building energy modeling with commissioning and EMIS, energy management and information systems, to optimize building system operations. Speakers today will be Marlin Addison of MS Addison and Associates, specializing in building energy modeling. Dotty Hage with MelRok, specializing in EMIS, energy management information systems, data analytics as well. And my name is Adam Williams. I am with Sindoni Consulting, SCMS, and we specialize in MEP systems commissioning. Marlin will start us off with a discussion on building energy modeling. Dotty will then present on energy management and information systems. I will then jump back in and discuss the combination and integration of BEM, EMIS, and commissioning to achieve and maintain the design performance intent of building systems, as well as further optimize building system operations. All of us here, or the vast majority of us here, are involved in one form or another of commissioning. So this will not be a presentation about everything you always wanted to know about commissioning. You're welcome. And I would say rather, it'll emphasize on the value of combining building energy modeling with commissioning, followed by EMIS with fault detection and diagnostics. And it will also include a case study presented by Marlin. I will then present a conclusion, and then we'll move into Q&A. And apologies, I should have started on that slide. So, keeping in order with the slides, for some reason, it's showing partially on my computer, but not on the screen. There. How's that? Screen early, screen late. We're good. Apologize for that. So, as I was starting to say, for those interested in earning AIACES credits, I think we're good. Thank you, sir. There is a test available through ACG. Obligatory slide. Objectives. So I would suggest that the primary objectives of today's presentation are, and I want to be cautious, to understand the synergy of building energy modeling, commissioning, and energy management and information systems with fault detection and diagnostics when assessing the design performance intent and optimization of building system operations. Additionally, to better understand the role of building energy modeling, BEM, during the design phase to establish the design performance intent, as well as during the commissioning and post-commissioning activities for evaluating and assessing the actual system performances. Finally, to understand how post-occupancy BEM and EMIS can be used to quantify and audit any drift from the Design Energy Use Intensity, or EUI. And on that note, I will turn it over to Marlin to address BEM.
Thank you. Not too loud though, right? Now that we adjusted that, we're okay? I won't shout at you guys then. So what's the context that motivated this? Like always, there's forever at these conferences, always something new coming over the horizon at us, right? In this case, what we've always done, validate, document, and ensure compliance with design intent, that's not new. But the scope of design intent is beginning to expand. Increasingly, the job now is becoming dictated by OPR requirements to include energy cost and environmental objectives as well. So there is more of a performance emphasis here that's whole building and long-term beyond what has been traditionally true. So that's what's peeking over the horizon, but our assertion is that that's already here and is within reach right now. Why did that do that? Well, that's curious. Okay, so what are the key questions now? Well, the first two here, is our design intent being realized, and is it being realized optimally? That's not new. But the scope potentially is, meaning performance focused. And as such, maybe we need to begin talking about not just design intent, but design performance intent, or if that's too much, we can just refer to it for short as not design intent, but performance intent. That is ultimately the objective, right? What, if anything, might be new in that broader performance-based context? Then, well, we ask, what are the long-term consequences of any deviations? If we say long-term, we're talking performance there, right? So how do we extrapolate from component level measurements and assurances of compliance with design intent at that to have we established the correct long-term performance intent? Was that ever identified correctly? And are we establishing it and reaching it correctly? We need to somehow look from both ends of this intent trajectory, that little arrow up there, right? We stand at one end, and if it's new construction or even retrofit at the design time, we have to establish what is our performance intent, what do we think we can achieve, and how do we know that we haven't left something on the table. Also the question, what are the costs of correcting the deviations? Well, if by cost we mean first cost or labor cost, what does it cost to correct the controls? That's not much. But there is a triage that has to happen as well, and that raises the question, if we don't correct it now, how will that cost accumulate into the future in terms of increased energy cost or whatever it may be? And in my case, what I think is particularly changing is who's accountable for the deviations, for the cost overruns, right? If we aren't hitting our emissions objectives, who is responsible? That means both who do we get to correct it? Do I pay for it, the client, the owner, or does somebody else pay for it because it was part of a warranty arrangement and so forth? So not only aggregating this to the bigger picture whole building, but at the same time being able to disaggregate it to each deviation, how much was that worth and who was behind that deviation, and did it get corrected satisfactorily? So new questions all with this broader context. So we've already asserted that our purpose here is to discuss BEM, I call it, but that may sound like building information modeling, BIM, so sorry that I pronounce BIM and BEM the same. I'm probably just going to talk about modeling, right? And if you hear that coming out of me, I'm a modeler, right? I'm an energy modeler. That's all that I know, right? I love associating with you folks, but that's not my expertise. I'm a modeler, right? So if we include this in an expanded commissioning toolbox, what do we get? Well, we get improved pre-handoff services, better precision, for example, improved post-occupancy evaluation, and that's really our example today, in particular, warranty phase things, and then better, more effective ongoing, and we might add here not just monitoring-based, but modeling-based commissioning as well. So with respect to building energy modeling, what's to know? I'm the specialist, you guys aren't. Maybe I can give you a little bit of background that'll help you appreciate a little bit more about why modeling is important. First, let's do that by making an analogy. If somebody comes to me and says, we want to model, I think, great. Is that the end of the discussion? I mean, and off I go? No, not at all. No more than if somebody comes to you and says, we need a control system. That's all of the discussion we need, right? Not even close. The industry exists because control systems need careful design and careful commissioning. Energy models, likewise, need careful design, and is there such a thing as commissioning the energy model? We normally call it calibrating it, but the answer is yes, there is such a thing, and it's important. So when we talk about building modeling, it's more common in my industry to think of it as whole building energy modeling or whole building. So what do we mean by that? Well, a building is always, no matter how large or small it is a collection of systems. More specifically, it's a system of systems, hopefully well integrated. If we talk about predicting whole building energy performance, then we mean that we are tackling the responsibility to understand and to predict the interaction between those systems, such as envelope, including fenestration, lighting, other things that control or influence internal loads, HVAC, and all the controls that interact and control these various things. So as an example, can we predict reliably the energy behavior and long-term consequences? By long-term, I mean not just an hour, but I mean a year or something like that, consequences of any one system, or worse yet, even one component within that system, without at the same time appreciating the state and the status and the operation of all the other systems with which it interacts. In other words, my answer is no, we can't do that. We have to take responsibility for that. That means we not only have to look at the whole building, but each piece of the puzzle, which means the whole puzzle. That's what building energy modeling is trying to accomplish with respect to whatever performance metric it's focusing on. Energy is what I will use as the example, but we'll be talking about emissions, other kinds of things, comfort, and so forth. So let me give an example that'll help us understand how I'm defining what I mean by interaction between components or systems. Let's say, for example, that as we're commissioning, we find that there needs to be an adjustment, I don't know, to a sequence or something that changes the operation of the airside economizer. What will be the outcome of that? How much has it been responsible for in contributing to our cost overrun or to our energy use intensity overrun, or EUI? Well, the impact of that airside economizer is going to depend on what is the code level minimum outside air in the first place. And does that code minimum change with CO2 sensing? If there's relatively limited amounts of outside air, then obviously the range of operation for the airside economizer is significant, and therefore its impact will be. But if we're in a building like a lab or a hospital where there's a greater amount of constant base load, if we might call it that, code level outside air, then the influence of the economizers doesn't have as much range of operations, won't have as much influence. In predicting the influence, obviously there's going to be a cooling benefit, so don't we need to know the chiller efficiency? But more important than knowing the design COP or kW per ton for the chiller, we need to know the part load performance of the chiller. Because if it's a non-integrated economizer, if it's an integrated economizer, so it is left with a duty at sometimes to not meet the load, but to help trim the load, then isn't the remaining chiller's responsibility to meet the remaining load going to put it at low part load? And knowing the full load performance of the machine is not nearly enough. And having some program with a default curve in it may not be enough either. We said hospitals a moment ago, is there humidification? Are we in the dry western part of the country, for example? Dry, cool air is a fabulous thing to relieve cooling requirements, but it can really do nasty things to your humidification requirements. And if humidification is electric, and depending on what kind of electric rate you have, you can kill yourself by using an airside economizer, right? Might have been better to go waterside or something. But how do you design the sequence to balance the potential penalties of increased outside dry, cool air, the penalties for humidification increases versus the cooling offsets? Well, building energy simulation accomplishes that. Is there heating involved or is there reheat? Because there will be penalties associated with that. And that's sensitive to other things such as the minimum VAV flow, splier temperature reset, and so forth. The fan energy is going to increase as you let more air side economizer air in. It's not as cold. It may not be 52-degree air. It may only be 56-degree air. So your fans are going to speed up and whatnot. How do you track all of that stuff? Well, the answer again is energy modeling, detailed energy modeling. And all of this becomes, and if there's only one thing that we do with determination and with effort to be correct, the most important thing to drill down on first is the utility rate. And using blended rates is almost always a big no-no, right? There are features such as declining block structures so that we're always out, and all of our ECM savings are out in that lowest, smallest, cheapest block, and we're going to overestimate the impact of our services if we do a blended rate. Heaven help us if we've got TOU circumstances and whatnot, right? Heaven's not here to help you, but the energy modeler is, okay? At any rate, it's a team approach. That's why there's three of us up here. Nobody's a specialist in all things, right? So the whole effort always and wherever will take a team approach. Will there ever be a time that tools like these whole building energy models will just be seamlessly, effortlessly stitched in to the FDD software? I don't think so, right? Every mechanical engineer wishes that they had a button on their keyboard that said the controls guy. They just hit that and the design is, boom, taken care of. Every architect wishes on his or her keyboard there was that structural engineering button, right? And oh boy, if we could just get that MEP button in there too, right? In 1962, a British guy named Sunderland proposed the concept of building information modeling, right? What we have in BEM models today, and said that we're going to tie performance models in that. He said it's going to take 10 years. That was in 1962. Do any of us have BEM models today that automatically integrate effectively performance? Well, how many years has it been since 1962? I think we're beyond the 10-year limit that we projected, so that's going to remain true. When will the architect have the structural engineer and the MEP button on their keyboards? The answer? Never, right? Because if that were possible, then the building owner would have an architect button on his or her keyboard and we'd be done, right? So it's always going to be a team effort, and so is our presentation today. So we talked enough about that. In addition to what I call interactive effects, there's something that's worth distinguishing called secondary effects. So the example here, consider that we've got something to do with lighting controls. Lighting controls, if we dim the lights or get them to turn off more than they should have or perform more effectively, presumably there's going to be reduced primary direct energy on that. It's going to reduce the internal gain, and from that there will be decreased cooling requirements, right? So there'll be a cooling benefit, but likewise a heating or a reheat penalty, and all of that again will come under the guise or the influence interaction with the electric rate or the whatever the utility types are. So 2 or 3 overarching functions of the building energy model. First, we'll talk about aggregation. That means we have to take the effects of all the deviations that we are tracking and correcting, hopefully to correct, add them together, but it's not just a summation, right? That's not, the formula is more complex than that based on the things we just talked about. In the process, therefore, we account for primary and secondary effects and interactive effects. So consider an additional role here that the building energy model can accomplish. If we take a well-calibrated, well-commissioned energy model, and we take it at handoff, meaning at design intent, and it's a good model, and we then measure deviations sometime in post-occupancy during warranty phase, and we find deviations and we stick those deviations and only those deviations into the model, no other changes to the model whatsoever, then compare the outputs from that model to the actual utility bill for the whole premise, right? The whole building utility bill. If they're a good match, how does that make you feel? Yeah, thumbs up. It also means that it is probably extreme. There will be cancellation, fortuitous cancellation of errors, otherwise known as central limit theorem, is everybody's good friend at this kind of a thing, right? It covers your butt on some mistakes that you didn't detect. But the likelihood is high that you've got reason to have high confidence that you have tracked down and accomplished all of the significant deviations, right? So there is, if you will, in addition or part of the aggregation function of building energy modeling, a checksum capability. I should have put a bullet up here for that. But if those things line up, then it says, hey, I have reason to have an encouraged, increased confidence in what we've accomplished here. Okay, the other thing then pretty obviously is that very often we don't have to wait a year in tracking our misconduct in the building, right, before we say what was a year's worth of misconduct worth. This extrapolates that on a timeline basis, right? We take short-term measurements, a few days, a few weeks, something like that, and then we can project it across the year, and we can project it to what a hot year or a cold year or a typical year or a future climate change year might be and so forth. That's all with the building energy model. Okay. So what's to know, what's to be mindful of, maybe careful about with regards to the shortcomings of building energy modeling? Well, first, let's acknowledge that by and large, the industry has far, 100 times more experience and application in design phase use of building energy modeling, right? As such, it has historically been more often adopted late in the process with intent simply to establish and document compliance with energy performance requirements, with energy code or with LEED or other kinds of systems, and it becomes just a scorecard, right? That has been what's been true historically. If it is adopted, I think probably now maybe 20% of the time, 25% of the time, it's being adopted earlier than that in schematic design, and as such, then it can actually guide the process. And as part of what we're here talking about today, whether this is new construction or retrofit, there is a time when the process undergoes design, and if modeling is involved at the beginning of that process, then you can establish more accurately what is an accurate, reasonable, and stringent, sufficiently stringent design intent. What would be your performance intent? What kind of EUI or life cycle cost are you trying to hit? Okay, with with design phase pre-occupancy, it is common practice to simplify maybe significantly, and what we're concerned about is maybe for purposes of including it in the CX toolbox, maybe oversimplified too often the BEM model itself. So that's done largely to reduce the cost of the modeling, also to reduce the runtime so you can turn it around, get quicker answers and whatnot. Codes like 90.1 at ASHRAE, the energy codes and so forth, LEED and other kinds of things, recognize this as a standard practice, and they try and limit it, the amount of simplification you can build into the model, because they want to preserve comparative value. Everyone who does that, and all the codes and whatnot say, this is not intended to predict energy use. Well, if it's not intended to predict energy use, why are we doing it, right? What it means is that we are going to try and just rank order from best to second best to third base what the ECMs are. But that'd be the ordinality of what we're trying to do. The cardinality of what we're trying to do says, are our numbers actually accurate? Is first place twice as good as second place, right? And is second place 10 times as good as third place, and so forth? These simplified models are not always adequate for that kind of a thing. EPA gas mileage rating level or label, do they still have that? I haven't bought a car in such a long time. Your mileage may vary, right? That's the intent with these simplified models. They may not be accurate, but they maintain comparative value. Not good enough for what we're talking about today. So be careful about that. That does not mean that you shouldn't do modeling in design phase. It just be more particular about how you go about it. So what are some of the differences in detailed or post-occupancy modeling in particular? You'll do much more detailed and probably even actual HVAC zoning without combining and simplifying that. Every single component in the building will be modeled, particularly pumps and chillers and boilers, not some kind of aggregation of those kind of things. Detailed scheduling, manufacturer equipment specific performance curves for that model of chiller and that model of boiler and whatnot. Not just under the standard conditions, but under the conditions you're actually operating it for. So you normally have to go back to the manufacturer for that kind of information. Detailed use schedules, detailed utility schedules, already stumped for that. Space by space differences when thermostats or outside air or internal loads or fenestration or shading differ from space to space with the building, not building averages, not oversimplified. And with that, I will turn it to Dotty.
Thank you, Marlin. So how does the energy management information system fit into all of this? I'm assuming that most of you guys are familiar with EMIS systems. If you're not, basically what it is it's a platform that's just going to tie into the BAS systems, metering, and then pick up all that information, or it can ingest data, from CSV files, etc. So it's just a platform that will pick up data from the different HVAC systems and then other like lighting and etc. And then it's going to provide that data in a way that you can trend, chart, etc. So the first big thing that an EMIS offers this process would be facility-specific fault detection and diagnostics. And the way we do it is we actually have our engineering go through all kinds of engineering designs, as-built plans, controls diagrams, and then what they'll do is they'll actually parse out the sequence of operation from those documentation, and then from tab reports. And Marlin touched on this a little bit, but like with chillers, for example, critical assets like chillers, we actually take in all the manufacturer parameters like evap approach, condenser approach, and those are critical because then they can give you an idea of how well that critical asset is working. And what we output is really, it's going to be facility-specific fault detection diagnostics, while we do have some generic rules, like if you're short cycling, you're short cycling. I don't need to know anything about your sequence of operation to tell you that your chiller is short cycling. But the biggest impact is really going to be your SOO, your tab, and chiller specific, so make, model specific rules. And then, obviously there's reporting, and that's going to play in heavily with commissioning. In addition to the fault detection diagnostics, there's a lot of cloud-based intelligence in EMIS systems. For example, fault detection diagnostics, I believe you presented yesterday on automated FDD. Good presentation, man. And so there's a lot of value there, because if you're doing like a trim and respond process or something like that, it can be a prolonged process. It's the more you automate, that's you're not spending, you're not doing any manual work to do that. That's going to help with the commissioning process in general. But in addition to automated function performance testing, with our platform in particular, we're able to do this because we have both read and write capabilities. But we have a lot of customers, especially in healthcare, pharma. They're demanding that we actually look at their portfolio of buildings and do a lot of analytics, because what we find is that when you design a system, everybody kind of adds their 10%. What you end up with is oversized ducts and oversized chillers and everything else. And so what we do is we actually take a portfolio, take data for a portfolio, for example, and then that in turn is used to inform the next design, like the next buildings that they're gonna design. And I'll give you one example. You may have airflow max set point. So the ducts are designed specifically for that. And then what we find is that the space temperatures are satisfied, and then you barely go above 50% of that value. So there's a lot of oversizing that goes on. So with cloud-based intelligence, you have a lot to play with. And a lot that you can do. Machine learning, this is a full-blown AI platform. And a natural product of this is ongoing MBCX. When you're sitting there and you're part of the commissioning process, and then you're ingesting parameters that are specific to that facility, this is a tool that you can use while you're commissioning, and our commissioning partner does that very well. But a product of that is a natural deliverable from that is ongoing monitoring-based commissioning, and that has a lot of value. And then this is a snapshot from one of our dashboards, and every rule that you see in here, with the exception of I think one or two that are generic rules, they're specific to that facility. So return air temperature at 65 degrees, when the return relative humidity is less than 55. So that's very specific to that facility. That same customer, you go to another facility, the sequence of operations is going to be different. And so what's the bottom line? What impact does an EMIS system have on commissioning and the project in general? Well, first thing it's going to do is it's going to reduce commissioning time, because you're automating a lot of manual labor, like analysis. You have automated data acquisition. I know one of the biggest struggles in this field is you have to go to either a controls contractor or you go to the BAS directly. You download the data, you upload to your analytics server, and then you have to. There's a lot that goes in there, like munging the data, etc., and it's very time consuming. So having an EMIS will allow you to automate the step of data acquisition, because you're talking to the BAS controllers directly, and then you're pulling that data directly from BAS controllers. Along with that would be all the analysis that you would normally do for fault detection diagnostics is automated. Then you have reporting, and now the process of finding anomalies, the root cause of the anomalies becomes a lot more automated. And then obviously there's a natural increase in the scope of deliverables. For example, if traditionally you would look at 10%, 20% of the terminal units, now you're looking at each and every one, and then you're prioritizing which ones to go after physically go up to that terminal unit and fix. And as Marlin mentioned, you can assign project team accountability, and then you have the ongoing corrective action and verification. On the project side, it's going to affect the three critical aspects of any project, which is the budget, the timeline, and the scope. And I'm showing some numbers from an actual project. And most importantly, for the owner, what impact does this system have on, or this process have on in regards to the operations and maintenance? The biggest one is obviously ongoing MBCX. Now you can have an in-house ongoing MBCX, and that's a big deal, because now you don't have staff running around trying to find what the root cause of the problem is, because a lot of times, when an anomaly is identified, the root cause is likewise provided. And a lot of times, technicians don't necessarily have the ability to figure out why a chiller failed. They may go up to the screen and do what they need to do, but here we're telling you failed because you failed on low pressure, and these are the conditions for why you failed on low pressure. And then obviously fault detection diagnostics, and then automated facility reports. These are specific to your facility. And so the biggest thing here is you're taking all the work that you're doing in commissioning, and then you're locking it into a platform, and then you're providing it to the owner to continue. And with that, I'll pass it back to Adam.
Yes, sir. We're at approximately 35 minutes, so I'll step it up a little bit. So Marlin gave us some insight into whole building energy modeling in both the design and post-occupancy phases. Dotty provided a comprehensive description of how EMIS and FD&D provide an additional automated, so to speak, check and balance, if you will, guide to the commissioning process and the retro commissioning process. So let's let's discuss the synergy between BEM, commissioning, and EMIS. So simply put, the power of an EMIS is at the component level. It helps us to quickly identify failed sensors, failed actuators where linkages perhaps have loosened from damper shafts or things of that nature, and quite frankly, deviations from sequences of operation. And I could, as Mr. Sindoni can vouch, I can go for 6 hours on detailed sequences of operation, because that is key to any successful optimization of building systems. Conversely, building energy modelings, or BEM's strength, is at the whole building level, and in that it provides a means to reconcile deviations of the measured energy consumption against the design performance intent. And it also extrapolates to annual energy and energy cost savings after optimizing system operations or achieving the design intent. Combining both with commissioning provides the tools needed to identify and validate deviations from the design performance intent. Now, typical goals of conventional commissioning. This is going to be a very high-level summary, 40-second slide. We're all familiar with these 4 or 5 items. Review of the contract documents. Sequence of operations is something that I specifically will spend a significant amount of time on, making sure I understand the design intent, identifying any technical questions for things that I don't understand. Where I see things that I don't think will work, I don't make that statement. I ask the question, hey, I don't see how your sequence is going to work, and let the engineer of record either tell me what I've missed or make a correction to the sequence. We again ask these questions based on a review of the sequence of operations. We also review pertinent equipment submittals to ensure that we understand how the selected system components will operate to achieve the design intent. Again, any questions that we have, we ask to the design team. Once all questions, of course, are answered, we develop system-specific functional performance test procedures for implementation by the controls contractor. We obviously identify any deviations from expected results. We track those deviations through resolution and closure, and finally ensure a successful turnover to the building owner. Everybody in this room pretty much is intimately familiar with that process, which is all great stuff. But here's the key. Integrating and combining BEM and EMIS, data analytics, provides a means to add design performance energy intent to the owner's project requirements, or the OPR, because the tools needed to quantify, assess, and evaluate system operations are already in place. Button. So, being able to add energy performance requirements to the OPR, as Marlin alluded to, effectively expands the commissioning toolbox. And it's on this basis that we believe the integration of BEM, commissioning, and EMIS allows for increased accuracy of pre-handoff or pre-occupancy commissioning services, as well as a more comprehensive list of commissioning services that extend through the initial post-occupancy period, warranty phase, prior to the expiration of the warranty phase, and into ongoing retro-commissioning services. With respect to benefits, my opinion, and I presume our opinion as well, the biggest beneficiary of combining and integrating BEM, Cx, and EMIS is the building owner. It provides improved access and immediate access to the control system. There is no need for the controls contractor to configure username and passwords for individuals. It provides early feedback on system operations. It's either working in alignment with the design intent based on what we see on trend logs. More often than not, we see a high percentage of systems that are not working in alignment with the design intent. And it's easy to implement, as I said, because the tools are already in place when you combine these three services. And perhaps most importantly, it holds the entire project team, from the design professional of record to the architect, the general contractor, and all of the subs, accountable for the design, the construction, the warranty, and ongoing system operations. Sorry, one more slide. So combining and integrating these three components, this is not an automated process. It's not automated yet. But it does provide the capability to perform a much more thorough assessment of post-occupancy energy consumption. As we know, building system operations can significantly drift from their design energy use intensity, or EUI. Proper integration, I maintain, of BEM, commissioning, and EMIS in a post-occupancy retro-commissioning scope of services provides synergy that can greatly improve detail, precision, and confidence, in particular, of optimization of building systems. It provides a means to audit and validate the drift from design EUI, energy use intensity, and it can also lead to a specific item-by-item retro-commissioning action items list. Again, the tools to do this are already in place when these three services are combined. It also creates a feedback loop with a multitude of information for use by the facility staff as well as the building owner. And finally, the synergy of integrating BEM with commissioning and EMIS helps project the future impact of selected corrective actions to impact in a positive fashion the whole building EUI. And at this time, I'm going to give it back to Marlin for a case study. I believe that that's where you're at. Sorry.
Okay, we'll be brief on the case study here and leave time for some questions. So this is a hospital edition. Med-surg, 90 beds, 3 ORs, compounding pharmacy, cafeteria. One of the things that was important to know, it's not only new construction, but it was design build. And before the RFP went out to the pre-qualified design build teams, there was a pre-design model combined with the owner's facility staff, the experience at other similar hospitals to identify a target EUI, which the design teams in their proposal demonstrated their ability to render a design that would accomplish that and then held accountable thereafter for the one who was selected. What was the post-occupancy data that was collected? And this was collected over about a 5-month period of time, not immediately following occupancy, but after things were pretty well filled up, I guess we'll say. Obviously, the on-site metered energy use, utility meters in particular there, EMS data such as supply return and mixed air temperatures, room temperatures, set points, airflows, et cetera. Cafeteria use was something we dug deeply into, talked with facility staff to get a better sense, not just that we can tell from the EMS system what was the operations for the fans and so forth, but what was their their bed count, how many people did they have, how many meals did they serve, how did they operate their flight dishwasher. There are a number of things like that we did as well. So the methodology is pretty straightforward. We first calculated based on the measured energy what the 4-month EUI is. We then used all of the data we just talked about to calibrate the model, extrapolate it to a full year. And then we went back and said, okay, from what we just learned, what would have been a reasonable adjustment to the expected EUI at turnover time, any corrections we want to make right there, and then what's the difference between those two things. A couple of slides here to illustrate the calibration phase of this. The middle part of the slide there is the calibration period, the 5 months. The total, the solid gray bars are the measured utility data for that. This one's electric, the next slide will be gas. The colored stacked bars is what the model is predicting, so we're saying that we're within what? About 1.5% of agreement on that for the calibrated period of time. If we then assume, okay, no other corrections, no other acceleration in the drift from what was expected, design intent, then what would the assumption look like? Here's what we do, the same thing for gas. That's a little bit closer to 2% error over that 5-month period of time. The only things, again, that we were allowed to change or that we committed ourselves to change is what did we measure? Anything that we might have thought later, oh, we might have done the model differently this way or that way, we didn't change. Only what we could prove based on measurements and interviews and so forth. Okay, here's a pretty complicated graph or something, so let me pause on this long enough to explain. There's a table at the top. There's a graph in the middle there. There are two conditions documented. The upper condition in the graph, there's a pair of bars that document that, is the substantial completion. The lower is as currently operated. So we might say that the substantial completion was as designed, design intent, and the lower one was, oops, that's what we're actually doing after 5 months of measured performance. So what happened there? In each of those two, we're reporting in the uppercase utility cost, which pertains to the blue horizontal bar at the top of the graph, kind of a thing. That's what's documenting utility cost. The bottom is UI, energy use intensity. What we ended up finding was that we overshot EUI by 45% and cost by 19%. How could they be so different? Well, EUI, as good as it is for a lot of purposes, is not great at predicting cost, not just because gas and electric always cost different. Electric always is more, or at least in my experience, always is more. But the way it renders down to a BTU per square foot basis, gas plays an overly important role. It has a very high opinion of its contribution to EUI, and it shows up, right? So in other words, look at the colors on both the upper bar and the lower bar there, what do we call those, substantial completion and currently operated. Look at the ones that tend to be reddish in color. That's the part that is contributing to EUI. But look at the cost amount above those and look at what a small fraction of that total cost is the gas cost. So at any rate, what we see here below the label there somewhere, I can't point to it, sorry, is that the gas energy increased by twice. It doubled, right? Whereas the the electric cost, the kilowatt hours went up by only 16% or so. So what was that attributable to? And this is the most important part of this, I guess, that we'll conclude with here, or almost conclude. There's two tables here, this one and the next page, right? This page, we start by saying there was design intent. That's what we were predicting. That's what the design builder was committed to accomplish. We looked at the various deviations, all the drifts and whatnot, and we categorized them into those things that were the owner's responsibility. Things like the head surgeon in the OR says, this is intense with fluoroscopy. What do you mean I'm going to set this to 68 degrees? I'm in here wearing a lead spacesuit. I want it to be 58 degrees. Now, who's going to say to that rainmaker, sorry, you can't do that, right? So boom, down it went, right, to 58 degrees. So in those cases, we say, well, that's owner responsibility for that kind of a thing. So to be able to separate that out, that's important, right? We had other set point issues there as well. Here, there's 5 rows, but it's really 4 things. The first one simply is there was a problem in the communications between the mechanical designer and the equipment manufacturer as to what did internal static pressure for the equipment actually include and what did it exclude. And it was the designer thought it included something that it didn't include. So basically, we couldn't maintain pressure the way it was supposed to. And that was exacerbated under economizer operations. So we lost the functionality of the economizers for the time being, right? Other things, supplier temperature resets were affected because there's a problem in getting, these were DX coils, there was a problem in getting humidification control. Part of that was that something for the pharmacy changed midstream in the code and whatnot, so that was of some concern and interest. What else do we have there? We've got, we eliminated some of the setbacks, and again, supplier temperatures and some of the VAV systems caused a big increase in gas consumption. So you can see the numbers there. It ultimately represented a significant overshoot of what they had projected and committed to. And with that, I think that's back to Adam.
So we have 10 minutes or so left. As Marlin alluded to in the case study, and as Dotty discussed, EMIS, combining building energy modeling with commissioning and an energy management information system, including FD&D, set up properly, provides the means to identify and validate and I would say quantify energy and energy cost savings annually based on post-occupancy retro commissioning services. It also, as mentioned earlier, essentially assigns project team, the entire project team, accountability for delivering on the project. It, as I said earlier as well, creates a feedback loop with a vast multitude of information for use by the facility staff and building owners. Ultimately, the integration / combination of pre- and post-occupancy building energy modeling, commissioning, and EMIS are significant pieces of the puzzle in our eyes that significantly enhance the capability, the ability, if you will, to achieve, maintain, and optimize building system operations and the design performance intent. And with that, I would suggest that in the remaining less than 10 minutes that we are ready to move into a Q&A, if there are any. Sir.
I got an easy one for Marlin.
That's perfect.
What I love energy modeling too. What's your favorite software to use?
The question was, what's my favorite simulation tool to use? Whichever one is the right one for the job. Is that a politically correct answer? I am biased because I'm one of the 4 developers of the eQuest model, of the eQuest tool. So that's the tool that I'm most familiar with. But I use Energy Plus a whole lot as well. And in fact, in about 50% of our projects, we start each project modeling both of those. We've got a capability where we model it in eQuest and then we automatically convert that to Energy Plus, and then we track them forward and resolve whatever the differences are. And that has been, it's like having 2 sensors, right? And neither one is correct. So anyway, that's a long answer to a short question.
Sir.
Question for Marlin. What is your opinion of the energy modeler also being the commissioning provider of the project?
I think that there's the question was what about having the energy modeler also being the commissioning agent? I think do you mean the same individual or do you mean the one company is that team?
Either or.
It's unlikely that one person has all the knowledge that 2 people that are specialists would. The others have made that point previously. I'm a strong believer that commissioning should be third party, right? And I'm because I believe that if the mechanical engineering firm, for example, has a division that does commissioning, to me that's a conflict of interest, right? I'm not saying that means that that's done unethically. I just mean that if I'm an owner my antenna go up and I smell conflict of interest. That doesn't mean I don't go forward with it, but that would be a concern. For me, modeling is exactly the same thing, right? If the modeling should be third party in the perfect world. I'm not sure if that answers your question entirely.
Yes, sir.
Again, reference to energy modeling.
So there are 3 guys in here that like energy modeling. The rest of you people are all commissioning people, right?
I play around in both.
All right, there you go. Ambidextrous.
Let's go. In the buildings that you have modeled, where you've gone back and made adjustments to the real world data that you received, have you had the opportunity when doing that to look at sub-metering data and really zone in on system level energy use and how that compares to what the model expected? Or is it just whole building energy use?
So the question is, when we calibrate the models, to what extent are we stuck with only whole premise, whole building, say utility metering, versus do we actually have sub-meter, maybe even end use separated out, electric meter, for example? I think probably in 2% of all of my projects ever, it's been what we would hope it to be. And in 100% of that 2%, the meters were never commissioned and it was all garbage. So it's been a huge, well, the 2% is a tiny thing, but it's been a huge disappointment, let's put it that way. So it's a real concern. So the more successful thing has been to go in with separate after the fact data loggers and put in some short-term measurements and that kind of a thing. So that's been done and it's done increasingly. So, but I've yet to see a case where end-use electric meters were installed and they were properly commissioned from the get-go. And in the cases that I've encountered, we can't shut those systems down to go correct it. So it's been a real disappointment. So it's a good question.
Is EMIS something y'all put on every job you commission?
Who's that for?
So I think that's becoming more common, yeah, with Sindoni.
I'd like to see that.
Yeah.
I think the collaboration, I think, is a good word. The combination of at least commissioning an EMIS provides 2/3 of the picture that I think we'll see moving forward in the industry. I also would suggest that I think the energy modeling, both pre-construction in the design phase as well as in the post-occupancy phase, will play a major role. I think that, again, the combination of BEM and commissioning, individually they all have strengths, but when you combine the 3, I believe that provides an exponential value, increase in value. And then I'm embellishing somewhat with the use of that word, but I believe it provides a significant improvement in the end product and ability for building owners to optimize system operations and hold the project team accountable. That's my personal perspective.
Yeah, and I think more and more building owners are actually asking for that because they do want to lock in all that commissioning work into a platform that then they can use or they can hire a third party to use for them. So it's becoming more and more common.
It's an evolutionary process that again, an opinion, but I believe that's the direction we're headed in.
One last question? Last question?
Cool. I mean, well,
There'll be time after as well, if you want
Fair
to
enough.
walk up. Yeah.
So one quick one is that you guys mentioned that you had a chance to actually calibrate the model. It's a new edition, right?
Correct.
And you went through only half the year, 5 or 6 months so far. Does that give you a 8760 calibration possible at this point, or are you just saying at this point, we're trying to see how close you are with the sensitivity analysis based on the output from for the utility data that you have available right now?
Let me try and summarize, see if others couldn't hear that. Was there an 8760 calibration performed, meaning the full hourly for the full year? And the answer is no. The only period of time we had the measured data for that we had to respond to where are we was with 5 months, so we extrapolated from there. Right.
And what was the sensitivity, I mean, like, what was the percentage that you were trying to dial it in, after adjusting for the deviation?
What was the agreement then after? Oh, it was about 1.5%.
How close you are?
About 1.5% over that 5 months. So
How much?
about 1.5%, a little less for electric, a little worse for the gas.
Wow.
All right, well, our time is up. We don't even have time for a Chris Jenkins buzzer beater. But thank you all for attending, and enjoy the rest of your day.